This video is all about quadratics and specifically extracting certain information from a quadratic. This is the graph of a quadratic. This is a shape. The shape is called a parabola. You've certainly, if you're in precalculus right now, you've heard this word before. You've dealt with these before. And if I ask the question like what things might I want to know or what things do we want to know about this graph, usually, right away, you say, I want to know where it crosses the x-axis. These are x-intercepts, right? And we know, depending on how much you know, these are also called solutions, or they are real solutions to this graph, to this quadratic equation that's represented by this parabola. And the other thing that you might point out if I ask that question is this little part down at the bottom, which is known as a vertex. In this orientation of a parabola where it opens up, this vertex corresponds to a minimum value. It's the lowest y value that you can get on this graph. And to be sure, like there are other things about this parabola that we in the overall like field of math and science, there are other things that we for sure would like to know about this. For example, there's a thing in every parabola in this kind of area, like right in here, called a focus. And that focus is related to how wide, how tall or kind of like wide or skinny a parabola is. And when we talk about parabolas in the context of something called conic sections, which is kind of like a design approach, then focus is like the main thing we really want to know about a parabola, the location of the focus with respect to the vertex. And why is that important? Well, when we do things like when we design parabolic things, like what are some parabolic things? Lenses are parabolic. There's certain parabolic mirrors that are used in like observing space, like telescopes. There are satellite dishes that are parabolic. All these kinds of things are really useful to us, and we utilize properties of the parabola, specifically like where the focus is, in order to like do things for us. So, but for the context of how we're talking about parabolas right now, x-intercepts and the vertex, these are the things we're really interested in. And if you've worked with quadratics before, you know that not all of them have x-intercepts. Like for example, what about if I had a parabola that kind of did this, right? It just opens down, clearly doesn't cross the x-axis anywhere. Well, it doesn't have any x-intercepts, but it does still have what are called zeros. And we have a bunch of different ways to find these things, which we're going to look at here in a minute. So these are the three different ways that you'll typically see a quadratic function represented. So, and I say quadratic function because specifically right now we're talking about y as a function of x and not x as a function of y. X as a function of y is not actually functional. It would be like an opens left or right quadratic. So these forms. This is the standard polynomial form. And what's good about this one is that you can easily extract A, B, and C for when you want to use the quadratic formula to solve for your quadratic. So this is good when trying to solve for x, and you're just going to use a quadratic formula. More useful though, in my opinion, are the next two. So this one here is called vertex form. And what vertex form is good for, you might have guessed, is for finding the vertex. The vertex here is just h comma k. It's literally this comma this. So if you're given a quadratic equation in this form, you can immediately identify what the vertex is, which is awesome. And then the third form here is called, shoot, I think it's called factored form. I could be off on that. Factored form, I think it is. And so what's good about this is that using the zero product property, like setting this equal to 0, allows us to really easily find where the x-intercepts are, or where the solutions to the thing are. Now, not every a quadratic can be factored, so we can't always get to this stage, but man, if we're given a quadratic in this form, that's awesome. We can immediately identify the zeros or the solutions, which is great. Now, we are going to talk about how you move in between these different forms, because it's clear like certain versions of these forms are easier than others in terms of like extracting certain information from them. There's one other piece of there's one other like drop of knowledge I'd like to give here. And it's not going to be something, it's not something we typically talk about in pre-calc, but it's an important idea for parabolas or for quadratics. And it has to do with something called Vieta's formulas, which deal with the sum and product of roots. The sum and product of roots. What does that mean? Well, what are the roots of this quadratic right here, right? The roots are m and n. So what Vieta's formulas say is that m plus n, the sum of the roots, is related to these coefficients of a and b and the constant of c. Now you should know that, because when you factor a polynomial, when you factor a quadratic, you have to account for a, b, and c when you're doing the factoring. So what does this mean? It means that since they're related, this is how they're related. Vieta's formula says that the sum of the roots is negative b over a, and the product, m times n, is equal to c divided by a. If you really think about that, it should make sense to you based on like what we know about factoring, right? Like two numbers multiply together to be c, right? And that's kind of, we have to consider that when we're factoring, and then two numbers add together to be b, right? Anyway, and then of course a comes into it, makes things more all complicated. Anyway, we're not going to talk so much about that, but if you are a student that's interested in like competitive math, like does math competition and stuff, Vieta's formula, sum and product of roots, oh man, it comes up all the time. Also, I would encourage you to go on YouTube and type this in Po Shen Lo quadratic. Like if you YouTube that, you'll find this very interesting video about using Vieta's formulas to easily factor a quadratic. And Po Shen Lo is a math professor at Carnegie Mellon University, so he's a genius, brilliant guy. So watch that video if you're interested. Anyway, we're going to move on. So now we're going to talk about the vertex form. So the vertex form of a quadratic equation looks like this, all right? And it's really nice because hk is the vertex. Now the thing is, I'm not always given the quadratic in this, I'm not always given it in this form. So how do we get to this form? We get to it by completing the square. So our old friend completing the square, it's going to look a little bit different here. I'm gonna keep this 7 kind of off to the side, and I'm just gonna look at these first two, and I don't like the 2 here. In order to complete the square, I need a 1 coefficient in front of my x squared term. So I'm gonna put 2x squared minus 4x. I'm gonna leave a little space to complete the square, and then I'm gonna put a plus 7. Now my objective is to complete the square inside the parentheses, so I'm going to look at the coefficient of that middle term, which would be kind of like b here. I'm going to divide that by 2, and then I'm going to square it. So negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So I'm going to add 4, and by adding 4 inside the parentheses, I've added a total of 8 to the right side of this equation. Now we learned that we have to then also add 8 to the other side of the equation in order to maintain the balance here. Or we can just also subtract 8 from the right side. If we both add and subtract 8 from the right side, we didn't do anything bad. We're just using this to manipulate. So to clean this up then, we'll have 2 times x minus 2 quantity squared, and then 7 minus 8 is 1, right? Negative 1. So here's my same function, but now it's in vertex form. So I can say that the vertex is at 2, negative 1. This is kind of something, just as a math teacher, I got to point this out. Something that's tricky for students is that it's not negative h comma k is the vertex, it's hk. So this is already giving you a negative, right? So you put h. It doesn't matter about this sign. If you had a plus here, in fact, you'd have to flip the sign and make it, negative. So if it was x plus 2 quantity squared minus 1, the vertex would be at negative 2 comma negative 1. Right, so completing a square is a really easy way to find a vertex. Right, what if we had this, right? This is a different equation now, but we're still going to complete the square here. I know this looks bad, just bear with me. So how would we do this? We would say, okay, just like before, a times x squared. If I factored out an a from b, it would be b over a x, right? Leave some space, c's out here. Now what would I have to add in here to complete the square? I would have to take b over a and divide it by 2, right? So b over a divided by 2 is b over 2a, and then I need to square, yeah, what I'm talking about. I need to square b over 2a, which would be b plus b squared over 4a squared, right? And if I add, so what did I add inside the parentheses? I added b squared over 4a squared. And I got to multiply that by a, so it's b squared over 4a. I have to now subtract b squared over 4a from the outside, right? Now I've essentially kept this all balanced here. And if I simplify this, this is what I have. A equals, f of x is equal to a times x plus b over 2a quantity squared plus this stuff, c minus b squared over 4a, whatever, right? Now, what we have here is kind of a yucky looking thing, but it is comparable in a lot of ways to this, right? Like these look the same, sort of, right? I have a thing being squared. So what we can say then is that, look, this h is equal to this positive b over 2a. This negative h. If negative h is equal to positive b over 2a, then h is equal to negative b over 2a. So negative b over 2a is the x coordinate of a vertex, right? And if I know, think about how a function works. If I plug in an x value, I'll get a y value out. So if I plug in the x value of the vertex, I'll get the y value of the vertex out, which gives us this. The vertex of a quadratic, of a parabola, the graph of a quadratic, is at this value. Negative b over 2a is your x value, or h value, and then whatever negative b over 2a evaluates into the function as. That's the y value, right? This here is like, I mean, if you're going to memorize something for dealing with quadratics, like do this. It saves you a lot of time. So if we're going to find the vertex of a parabola, it's either of these two things, right? We can complete the square. If we're given this, you don't have to worry about negative b over 2a. It literally tells you what the vertex is, hk. But if you are given ax squared plus bx plus c, boom, negative b over 2a, you don't have to worry about completing a square to find the vertex and stuff. So two different ways to get this very important piece of information about a quadratic, or the graph of a quadratic, and that is the vertex. Okay. The other thing that we like to know about parabolas are their x-intercepts. So these are zeros, like actually real number solutions. Now, keep in mind there are such things as non-real number solutions to parabolas. That's when we have an I, right, in our answer. You've for sure used the quadratic formula and got an I out before, right? So answers that have I in it. That just means that this parabola doesn't cross the x-axis. But there are three ways to find the roots or the solutions to a quadratic, the roots of a parabola, and they are. I would argue that these are in order of complexity from least to greatest. Factoring is always going to be your easiest if you can factor. Completing a square is nice, and then you have to like square root both sides to solve for x, or just the quadratic formula. Okay, and so let's look at kind of maybe some opportunities, some different ways, like when would we maybe want to use each. So here is actually the same quadratic represented in three different ways, right? We have the top version here is in factored form. Factored form is so nice for finding zeros, right? All we got to do is set it equal to 0 and solve for x. So if 3 times 0 something times something equals 0, I know 3 doesn't equal 0, so it's not 3. Right? But x minus 2 could equal 0, or x plus 1 could equal 0, which means x is 2 and x is negative 1. Both of these values would make my, if I plugged these values in for x, my y value would be 0, meaning those are x-intercepts. So my solutions here, my x-intercept, well, it depends how you want to write this, right? The solutions are that x is equal to negative 1 and 2, right? Or the x-intercepts themselves, that's asking you to provide a point, and those points would be negative 1 comma 0 and 2 comma 0. All right, what about this one? If I want to find the roots for this, well, I'm just gonna, I'm gonna set this equal to 0, but then I have to manipulate and do a square root thing. So if you're given in this form, in vertex form, you don't have to like do anything crazy here. You're just gonna do your math that you know how to do. So if I add 27/4 to both sides, right? So we'll have, let's do that, hold on. So we'll have 3 times x minus 1/2 quantity squared plus equals 27/4. We're going to divide both sides by 3. What we're going to have then is x minus 1/2 quantity squared is equal to 9, 9 divided by 4. Then we square root both sides, and we'll get that x, now I'm skipping a step here where it's the absolute value of x minus 1/2 is equal to 3/2, but it's plus or minus 3/2 here, right? X minus 1/2 is equal to plus or minus 3/2. So you'll find that the answers are still -1 and 2, right? If you complete that. And then lastly, this one, how do we do this? Well, here really we can use the quadratic formula if you wanted, right? X is equal to negative b plus or minus the square root b squared minus 4c all over 2a. I only learned that jingle very recently. But you can do that, or you can factor this. This is pretty easy to factor. X squared minus x minus 2, right? It's -2 and 1, so like you can factor it. And this is one where I wouldn't bother with the quadratic formula, but just illustrating that, you know, if you're in this ax squared plus bx plus c form, the quadratic formula is pretty convenient, especially if the numbers are gross and it doesn't factor. All right. So here's just an example problem, right? What if I wanted to find both the x-intercept and the vertex of just random parabola I came up with? So we're given this in ax squared plus bx plus c form. So it is actually really easy. We'll show 2 ways to find the vertex, right? We know that the vertex is at negative b over 2a and then f of negative b over 2a. So let's see how you would go about using this idea just with this standard thing here. So I can say that the negative b over 2a is equal to, like literally, b is equal to 36, a is equal to -2, and c is equal to -160. I know we don't need that, but whatever. Okay, so negative b means -36 divided by 2 times -a, which is -2. So what is -36 divided by -2? 9. So 9 is the x-coordinate of the vertex. If I then wanted to find the y-coordinate, I would just say, okay, what's f of 9? Right, so it's -2 times 9, -2 times 9 squared plus 36 times 9 minus 160. Yeah, I have no idea what this is. So -2 times 81, that's -162. 36 times 9. Oh my gosh, I don't know. Is it? I'm literally using a calculator here. 36 times 9, 324 obviously, minus 160. So is this just 2 minus 162 minus 160? Yeah, it's just 2. So the vertex then is at 9, 2. Easy, right? So that's negative b over 2a. The other method, of course, would be to complete the square. So we can also do it like this. F of x is equal to, f of x, sorry, is equal to -2. I'm factoring -2 out of this stuff. So x squared minus 36 divided by 2 is 18. X, leave some space, and then -160 out here. If I added, so what do I, -18 divided by 2 is -9 squared plus 81. So I need to say -2 times 81 is -162. So I have to add 162. So then I'm going to end up with this, -2 x minus 9 quantity squared plus 2, right? Look, there's your vertex form. And again, look, 9, 2, HK, that's your vertex. So 2 different ways to find the vertex. And then to find the roots, well, factor it or whatever. If we already bothered doing this, we can find the roots really easy by subtracting 2 from both sides and then square rooting. Or we could factor this, right? So -2 comes out, we have x squared minus 18x plus 80. So what multiplies together to be 80 and adds or subtracts together to be 18? 10 and 8, right? Both negative. Well, so we skipped a step here. Divide everything by -2. 0 is equal to x squared minus 18x plus 80, right? this will factor to x minus 8. I'm kind of getting on top of myself here. X minus 10. So x could equal 8 or 10. So the roots or the x-intercepts of this parabola then are 8 and 10. And you can always go back and check these things, right? You can come back and plug in 8 and plug in 10 just to verify that you're going to get 0 out. And you'll find that you do. This will be negative 200 if you plug in 10. Negative 200 plus 360 minus 160, yeah, that's 0. And you can do it for 8 also, but 10 is easier than 8. Anyway, so that's how you find either the x-intercepts or the vertex. Now the only thing, or both, the only thing that's left in this kind of section is how do you apply this to real world problems. So I'm going to just have one quick example here in this video, but there will be a separate video where it goes into depth about applying these ideas to real world problems where you're trying to find maximums of like profit and stuff. Because ultimately we're talking about functions, and what's the use of functions if not to predict things, if not to kind of come up with a plan on how to maximize revenue or profit or production of something, or maybe you're looking to find out what the maximum height of like a object can be, or you know. So let's just look at a quick word example and then keep your eyes open for another video that talks about more in-depth examples and more difficult examples for using quadratics. Right, Tommy Pickles and his gang of misfit toddlers are making a power grab on the playground. They have 300 feet of playpen fencing that they want to use to enclose a maximum possible rectangular area. One side of their enclosure will be the wall of their kindergarten building. What are the optimal dimensions of the playground enclosure? Okay, so let's draw this picture, right? Here's their kindergarten building, and they have some fence, and they want to make a rectangle out of it. So it's got to be something like this, right? And they have 300 feet of fencing. So we don't know what the dimensions are going to be, but we want to maximize these dimensions. So we know that that we want to maximize the area. So what is the formula for area? It's length times width, right? Well, what are the lengths and the widths? I don't know. Let's say that this dimension is x. If it's a rectangle, that also means this dimension is x. And if they had a total of 300 feet, well, we just use x of it and another x of it, which means left over, this is going to be 300 minus 2x. Okay, so these are the dimensions, right? But we don't know what x is, so we have to figure that out. Now, what's going to happen here? Let's just do a quick little thought experiment here. If I had a big rectangle that looked like, or like a big, tall, skinny rectangle, and let's say like this was one, let's say I had a total of 30 feet of like length I can use on the sides, right? If this was 1 and this was 1, that means I have 28 left over. Divided by 2, this would have to be 14 and 14. What is the area of this? The area of this would just be 14. Okay, if I instead I had again 30 like whatever is of length to use for my rectangle. If I made this 2 and I made this 2, then we'd have 2 and 2, which is 4, 26 left over. I mean, this would be 13 and 13. Well, now the area of the second one would be 13 times 2, or 26. So it increased. And you can think, if I keep on increasing this dimension, I'd have to decrease this dimension. But at some point, I would establish a maximum area. And then as soon as I got past a certain amount, I'd have this sort of shape that looks like this, and my area would start to decrease again. So think about what that means. If I had a graph, right? If I had a graph where this is the area and this is the width, like let's say this is the width, then this graph would look something like this over time. And I want to know then, I'm trying to find the maximum here. So we're going to use these dimensions on Tommy Pickles' playground playpen, and we're going to find the maximum possible area as a function of x in this case, because we call it the width x. All right, so let's do that. Let me erase this stuff. And we're just going to write the function of area as a function of x, right? It's literally just going to be length times width. So x times 300 minus 2x. Now this isn't a particularly useful form. If I wanted to find the zeros of this, yeah, easy, right? 0 and 150. So if I want to find the maximum, a maximum, that's the vertex. So we're going to multiply this out, and we're going to get a of x is equal to 300x minus 2x squared. If we rearrange this into standard polynomial form, where we have decreasing orders of exponents, negative 2x squared plus 300x, like plus 0, right? Well, remember what we want here. We want to know what the maximum is. And specifically, we want to know what x is. So if we think about that, right? This is an area of his playground. We want to know, what do I have to make this value in order to establish that maximum area? Okay? So I just need to find, remember, vertex is at negative b over 2a, comma, f of negative b over 2a. So what are the optimal dimensions? I want to find negative b over 2a. So look, a is negative 2, b is 300, right? So negative b over 2a is negative 300 divided by negative 2 times 2, which is 75, which means that x needs to be 75. And if x is 75, like let's look at what we drew over there, right? This is 75, this is 75, and altogether it's 300, which means left over we have 150. So optimal dimensions are 75 by 150. That would yield the maximum area. And you're like, man, that's not a square though. Yeah, you're right, it's not a square. It is the case that the maximum, given a set perimeter, the maximum area of a rectangle is going to be a square. But the thing is, the wall of the kindergarten building is what messes this up. So anyway, that's how you can use these ideas of a parabola to like solve this is obviously a very important problem. Tommy Pickles and Charlie and Phil and Lil, and absolutely not Angelica. They're it's important. They're a good gang. They need to have their space on the playground. Anyway, watch for my next video about using these ideas to solve even more complicated quadratic application problems.